Hi everyone. In class on Friday, we focused on two types of quantifiers: universal quantifiers for all items and existential quantifiers. There exist items. We also talked earlier in the week about the importance of conditional statements. What we're going to finish up with today is just the connection between conditional statements and quantifiers. On the Quantifier Worksheet, which is posted in the assignments folder, problems 3 and 4 focus on this connection. Here's a statement of the problems. On the worksheet you have question 3, then you have a number of statements, then question 4 asks about these statements in question 3. Here's one of the examples. Question 3a says, if a quadrilateral is a square, then the quadrilateral is a rectangle. Okay, this statement is not saying that if you have a particular quadrilateral that's a square, then that quadrilateral is a rectangle. It's saying for any quadrilateral that's a square, that quadrilateral is a rectangle. So question 3a, and question 3 says write each of these conditional statements as a generalization. Okay, so I'm going to bring my pen up. And question 3a is basically saying if the quadrilateral is a square, then the quadrilateral is a rectangle. You're really saying that for all squares, or for all quadrilaterals. So for all quadrilaterals, if the quadrilateral is a square, then the quadrilateral is a rectangle. Alright, so basically what we've done is we've quantified this statement. We're talking about all quadrilaterals. Now, question 4 says for each of the statements in question 3 that you think is false, write the negation, and then after you write the negation, demonstrate why this negation is true. Remember that the negation of a universal quantifier is an existential quantifier. So if we had this statement and we wanted to negate it, we'd say, instead of for all quadrilaterals, we'd say there exists a quadrilateral. Such that, or remember the symbol for such that is a backwards E, like that. Now, the negation of P implies Q, which we focused on Wednesday, is P and not Q. So we'd say P, the quadrilateral, is a square. And the quadrilateral it's P and not Q. The quadrilateral is not a rectangle. So if our original statement we'll call S, then this is the negation of my statement. If we think S is false, then we think that the negation of S must be true. In this case, for all the quadrilaterals, if that quadrilateral is a square, it turns out it is a rectangle. So the original statement is true in this case. Okay, let's go to the next example, which was 3c. The question says, if n and m are positive integers, and n is less than m, then 1 over n is greater than 1 over m. Okay, so again, it says if n and m are positive integers, not just two of them you can think of, but for any positive integers. So to quantify this statement, I'll do this one in blue, we'd say for all integers, n and m, for all n and m in the integers. If n and m are positive, so we'd say if n is positive and m is positive, and n is less than m. So it's a fairly complex hypothesis for this conditional statement. Then what do we know is true? Then 1 over n is greater than 1 over m. Okay, so if n and m are positive integers and if n and m are integers, if n is positive and m is positive and n is less than m, then when we take the inverses, 1 over n is greater than 1 over m. Again, that's a true statement. If we thought that that was false, we'd have to say, what is the negation of that statement? Negation would be there exists an n and m in the integers, such that p and not q, so such that n is positive and m is positive and n is less than m, so that's our p, and not q, so and 1 over n is less than or equal to 1 over m. If we could show that this existential statement is true, that would be a counterexample. Again, we'd show that by finding n's and m's that make this true. That would be a counterexample which shows that the original statement is false. Finally, this focus on a statement that is false that we can construct a counterexample for. So here's a question. It's 3h. Okay, the statement is if x is less than z, then x squared is less than z squared. This is a little bit vague because we don't know, are we talking about integers? Are we talking about natural numbers? Are we talking about real numbers? What are we talking about? I'm going to go ahead and just quantify it and say, let's focus on a particular type. Let's focus on real numbers. So to quantify this, and it turns out if you think about this statement, it's going to be true for some things but not true for others. It turns out that if x and z are natural numbers, counting numbers, so natural numbers are 1, 2, 3, and so forth, then the statement is a true statement. Okay, 2 is less than 4, 2 squared is less than 4 squared. But for integers we get in a little trouble. So let's focus, just for the sake of argument, let's say that we quantified this. We said that for all x and z in the integers, if x is less than z, then x squared is less than z squared. So I've added a quantifier to this statement. For all integers x and z, if x is less than z, then x squared is less than z squared. That's our statement. We'll call our statement S. The negation of S would be there exists an x and z in the integers such that p and not q, so x is less than z, and x squared is greater than or equal to z squared. Okay, I think the negation is true in this case. And the negation would constitute a counterexample. A counterexample, remember, is an example that shows that a generalization, a universal quantifier, a statement that has a universal quantifier is false. So there exists. That's our example. So let's come up with this example. In this case, let's say x equal -4 and z equals 1. Okay, so first of all, again, and this is the explanation I'm going to be looking for. want you to show me that this negation is true. So we know that x and z are integers, so they're elements of the integers. Let's see, negative 4 is less than 1, so x is less than z. Okay, and what else do we need? We need x squared is greater than z squared. Well, let's see. Negative 4 squared, which equals 16, is greater than negative 1 quantity squared. Oh, excuse me, positive 1 quantity squared, which equals 1. Okay, so there exist integers x and z where x is less than z, but x squared is, x squared is greater than z squared. Actually, it's greater than or equal to z squared. So, since we found x and z that are integers where x is less than z and x squared is greater than z squared, that says that the negation is true and the original statement is false. Our counterexample, x is negative 4 and z is negative 1. That constitutes our counterexample. Okay, the explanation here says this is why the counterexample works. Okay, for your homework, again, for the weekend, focus on the MIU video and finish up through problem 4 on the Quantifier Worksheet. Have a great weekend, and I'll see you on Monday.